So we're going to talk today about energy and a couple different kind of sectors of energy. But energy is one of the most important concepts we learn about in science, right? It's kind of the base of everything we learn about, okay? And what do we know about energy? Can't be created or destroyed, 1 for 1, okay? We already decided Kelsey's answering every question today in class, so she's 1 for 1. Okay, I'm just kidding. All right, good. Can't be created or destroyed, so it is conserved, okay? There's several different types of energy that we are going to talk about, but we're going to hit on two pretty substantially, okay? Can anyone think about a couple different types of energy we might learn about? Kinetic, good. Potential. Those are our two main ones, okay? This chapter we're going to look at kinetic energy and potential energy. Okay, those are our two bigs. Okay, so when we talk about energy in physics, what energy means is, in and of itself, it's the ability of an object to perform work. Okay, the ability of something to perform or even withstand or whatever. Okay, the ability to do work. So what does work mean in physics terms? What's the equation for work? Times displacement or distance, right? So, and we don't really have to even think about it as force parallel. We just need to make sure we think about it as a force applied over a certain distance. However, that force does need to be parallel to the displacement that's happening, okay? So work is equal to force times displacement. We apply a force over a certain displacement means work has been done, okay? If work has been done, that means energy has been transferred, it's been transformed into something else. There's all these things are connected. Okay? So kinetic energy is the energy of something in motion, right? Where do we see that kina in other things in physics? Where have we seen that before? In our kinematics equations, which are all about motion, right? So these are the energy of an object that's in motion. Kinetic energy is transferable. Okay, so it can be transferred from one object to another. And this is kind of what happens when kinetic energy is transferred. Okay? Yeah. Mm-hmm. When one object exerts a force on another, and the second object has been moved a certain distance, we consider work being done, right? So when I exert a force on my iPad and it slides, a certain displacement or a certain distance, I am doing work on my iPad, or the iPad is having work being done on it. That also means that I am transferring kinetic energy from myself to that iPad or to that object, whatever I'm pushing. Okay? When we solve for kinetic energy, here's the equation that we're going to use. Okay, so this needs to go on your equation sheet. Okay, if you need a new one, or if you haven't gotten a new one, there's some up here, you can grab one. But this is the big one. You could also just write this as K subscript E if you want to. Okay. K subscript E. Wow, all right. K subscript E. It doesn't have to be too big capital. It doesn't really make a difference, honestly. Okay, we're going to combine a lot of equations and put that in there, but kinetic energy is 1/2 mv squared. What do we think the M probably stands for? Mass. Good. Mass has to be measured in what? Kilograms. Not grams, not centigrams, not pounds. Has to be in kilograms. And then V would probably be what? Velocity, which has to be in meters per second. Okay, so kilograms and meters per second. What would we guess that energy might be measured in? What would the units for energy maybe be? Joules, good. Okay. A little note here about translational kinetic energy. When we say something is translated, okay, in geometry, what's it mean to translate something? Just to slide or move it, right? It's not rotating, it's not doing anything else. So translational energy are things that are not spinning, okay? They're just moving from point A to point B. Okay, so when we talk about this kinetic energy, it's things that are not being rotated. We're not looking at that spinning component of it, but it's just things that are pretty simply moving from point A to point B. Okay. So we've talked about work and energy being connected. We're going to be able to use this equation that we take the net work of a system is equal to the change in kinetic energy. This has a really, really fancy name. Okay, it's called the work energy principle. Okay, so what that's telling us is that the net work on a system is equal to the change in kinetic energy. So what's the 2 subscript mean and the 1 subscript? Yeah, final minus initial. You could put an F and an I there if you wanted to. But it means final kinetic energy minus initial kinetic energy. So if an object's at rest, how much kinetic energy does it have? 0. Okay. It's not only the energy of an object in motion, but if we do it mathematically, we plug in 0 for our velocity, 1/2 mv squared would give us a 0 kinetic energy. Okay, so we need to pay attention about that if the object's in motion or if it's not. Okay? When we use this work energy principle and we use this equation, we can't use just like the work done by friction or the work done by the applied force. It has to be the net work of the entire system. Okay, so when we're looking at the work, it has to be of the entire system. So just pay attention to that when you're plugging into this equation. It's got to be the work of the whole system. What is work measured in? Joules, which means kinetic energy also has to be measured in joules. All right. Sorry, do we have what we need here? Okay. This is a couple just kind of short explanations about the work energy principle that are really pretty common sense, right? Tells us if that positive work is done, that means kinetic energy has been increased, right? You don't even have to write this part down. I just want you to think through this, okay? If we've got a positive net work, that means that our kinetic energy final is greater than our kinetic energy initial, right? Because that's what it is, delta kinetic energy. So if we have negative work done, what does that mean is happening to the kinetic energy? It's a loss, right? There's a loss in kinetic energy. So the object's probably slowing down, okay? So a change in work that is positive might mean that we're gaining speed, right? Or we're gaining kinetic energy. Negative work means that we are losing kinetic energy or our object might be slowing down. If no net work was done on the object, that means that our kinetic energy has remained constant, okay? So if we've got no net work, that means we have no velocity, right? We're not moving anywhere, or it's staying completely the same, right? Our net force might be equal. Our net force might be 0, which would lead our work to be 0. Okay, measured in joules, just like work, we talked about that. Kinetic energy is scalar, so what's that mean? It does not need to include. It does not need to include direction. Okay. Questions on this one? All right, pretty self-explanatory. Let's try one. Need your calculators out today. Okay, so we know kinetic energy is 1/2 mv squared. Work is equal to change in. If we know our initial kinetic energy was 0 because it started from rest, what does that mean our final work is equal to? Good. 45.3. What's our units here? Joules. Okay, even though work is a scalar quantity, right? What if our final kinetic energy was less than our initial kinetic energy, right? That would give us a negative net work, That's okay. You can include the negative. It's just not something that is 100% necessary all the time. But if your number comes out negative, just include it. Okay, I know it's scalar, so I know it doesn't technically need that direction. Go ahead and include it if it's a negative that comes with that. Okay? All right. Okay, good. How much work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Okay, so how much net work is done to complete this? Okay, so we know that work is equal to change in kinetic energy, 1/2 mv squared minus 1/2 mv squared. Our final velocity here is 30 meters per second. Is that what we had? 250,000 joules. If I want to put that in kilojoules, what would my answer be? 250 kilojoules. Okay, because kilo means 1,000, right? So all we're doing is moving that back over. Does that make sense how we did that? Okay. Don't try to shortcut that, right? Take it 1/2 times m times, v final minus v initial, right? That square is going to throw it off a little bit. Okay. All right. Let's move on to potential energy. There's a couple different kind of subcategories of potential energy. But essentially, potential energy is associated with its location. Okay, so potential energy, and specifically this is gravitational potential energy right now, but potential energy in general has an association with the object's position. Okay, so it depends on the position or configuration of the body and the surroundings. So what does an object have the potential to do? Okay, that's what we're kind of looking at. If an object is held high above the ground, what does it have the potential to do? It has the potential to fall, right? To fall on something and therefore do work on an object that it would fall onto. Okay? If I have a spring and it is compressed, what does it have the potential to do? If it's compressed, what does it have the potential to do? Right, stretch. It has the potential to get back to its original position. So those are some examples that we're going to look at. We're going to look at gravitational potential energy and spring potential energy. But you need to understand potential energy has to do with where the object is located. What does it have the potential to do? Okay? The first major form of potential energy is gravitational potential energy. So what are we doing to overcome gravity, right? We have this potential once we get at a location above the surface of the earth to fall or to drop, right, due to gravity. Okay, when a heavy brick or any object is held in the air, it has the potential to do work on an object on the Earth's surface. It has the potential to transform energy into another object on the Earth's surface. Those are things that we need to think about. Okay. You can shorten these up. You don't have to write them word for word. But just understand, as something gets higher and higher and higher and higher above the earth, it has more and more and more potential energy. Okay? Because let's think about something. If I hold an object 1 meter off the ground and it falls, right, and hits, let's say, a nail, it's going to drive that nail into the ground a little bit, right? If I hold something 10 meters above the ground and it falls and drives that nail into the ground, it's probably going to hit it with a little bit more impact, right? And it's going to drive that nail farther into the ground. Can we visualize that and conceptualize that? So as it falls farther, right, gravity picks up more, allows it to pick up more and more speed, right? It accelerates as it falls, and it's going to hit that object with more force, which would therefore drive it a farther distance, right, which would mean more work is done on it. So as it gets higher and higher in the air, it gains more and more gravitational potential energy. Does that part make sense to us? Okay, good. So here's our equation for gravitational potential energy. Okay, mgy. M is equal to mass, gravity is equal to 9.8, and y is equal to the height. Okay, y is your distance, right, your height. Since energy is a scalar, and since we're looking at the work being done to overcome gravity, your gravity here is not negative 9.8, right? It's just the value for that acceleration due to gravity. You don't have to plug in the negative, okay? I know that's a little bit kind of difficult to understand, but as we climb that height, we are gaining potential energy. We want that to be positive, right? We're gaining upward potential energy. So G is always 9.8. Y is the height above the Earth's surface. M is the mass, which has to be in kilograms. Okay, higher off the ground, the more potential energy it has. Work done by gravity is the change in potential energy. Okay, so you can keep that here. Your book includes the negative for the work done by gravity just to show us it's going in the downward direction. Again, not a huge deal if we keep that negative or if we don't, but your book does include it just because it's the work done by gravity, which is going in the downward direction. That's not going to be that big of a deal for us as to whether to include that negative or not, but your book does include it, so I put it in there. Okay. So work again is is equal to a change in potential energy. Okay, so mg times y1 minus y2. Here we can abbreviate that problem a little bit because there's no square that's going to throw us off. Okay, so at point B we went up, which means we gained potential energy. Let's say if we went from A to point C, we're going in the downward direction, which means we might lose potential energy. Okay, we're still saying m times g times y, which would in this case be what? Negative 15, right? Because we're landing 15 meters below where we started. Okay, so here we're saying there's a loss in potential energy of 147,000 joules. Okay, from point A to point C. Questions there? Pretty simple? All right, good. What's the change in potential energy when the coaster goes from point B to point C this time? From point B to point C. Okay, we could do this a couple different ways. The simplest way would just be to subtract, right, our final minus initial potential energy. Okay, so change in potential energy. Oops.
You leave the negatives out. Put the negative on the...
I would keep it, right? If you're starting out with a negative potential energy, I'd keep that. Right, so negative 147,000 minus 98,000. So the total change okay, so when we started at point B, we had 98,000 joules worth of potential energy. By the time we dropped 25 meters to point C, we have now a total of negative 245,000 joules of potential energy. So we lost that much. Okay, another way that you could do that, that would be just as simple, would be to take m times g times negative 25, since that's how many meters we fell. Okay, and that would give us the exact same answer. Okay, as long as you look at the difference in height between those two things, you would get the same answer. Okay, questions here? All right, pretty simple so far. All right, a couple other types of potential energy, or the one other main type we're going to look at is in elastic materials or springs and coils. Okay, we're going to look at what the potential energy of a spring or a coil might look like. Okay, so there's a whole separate equation for the potential energy of a spring. But we need to outline kind of what a spring looks like and what it acts like here. Okay, so on the left, this picture is of a static spring. What's it mean for something to be static? At rest, good. So if it's static, that means it's not being compressed or stretched. It's just sitting, not doing anything, right? So a static spring has no stretch one way or the other. Okay? When we push or squish the spring together, that means it's being compressed. If we stretch it, that means we are stretching it out. Okay, so those three terms altogether, you need to be familiar with what's happening in that spring. Okay, so stretched or compressed. All right, potential energy of an elastic spring. To stretch or compress a spring, we have to exert some sort of force on that spring. Okay, so the force is by the person. You don't have to put that subscript there. Okay, the force that is being exerted on the spring to move it a certain distance can be found using this equation. Okay, K times X. And I'll explain what those variables mean here in a second. But essentially, in order to stretch or compress a spring, we have to exert some force. Okay, usually by a person, but some force has to be exerted to stretch or compress the spring. And that can be found by taking K times X. All right, K is what we call a spring constant. We haven't talked about spring constants at all in here yet, so this is our first encounter with spring constants. Spring constants are just that, they're a constant, okay, except not really. Every spring has its own spring constant. And what the spring constant tells us is how basically tightly wound that spring is, how easy it is to compress or stretch. Okay, so there's very, very differing degrees of spring constants. Okay, some are really easy to stretch, some are really not. Okay, what do we think the spring constant units might be? Think here. X is our displacement, and what's that measured in? And what's force measured in? Newtons. So if we solve for K, newtons divided by meters. If we solve for K, we need to divide X over, which would leave us with K equals force over displacement. Okay, which means the units for K should be newtons divided by meters. Okay, do we see how we got there? Okay, so the units for K are newtons divided by meters. That's a spring constant. The greater the spring constant, the more difficult that spring is going to be to stretch or compress. The smaller the spring constant is, the easier it is to stretch or compress. Okay, this is a big equation that you should probably have on your equation sheet, is F equals KX. Okay, kind of the reciprocal to this, right? If the person has to exert a spring to stretch or compress it, the spring also itself has to exert a force to get it back to its static state. Okay, so the force exerted by the spring is equal to the opposite of that force, right? Equal and opposite forces. That's why we have a negative in there. Okay, so the person exerts, 30 newtons to stretch it this far. That means the spring itself is exerting another 30 newtons back in the opposite direction to get it back to its static position. Okay, that's Newton's third law right there. Okay, so usually the force exerted by the spring is going to be the negative of that original. Okay. This is usually known as the restoring force. Why would it be called the restoring force?
Restoring it back to its original.
Good. We are restoring it back to its original static position. Very good. Restoring force. Okay, this equation right here, these force equals kx, is called the spring equation or Hooke's law. Okay. So in case you're on Who Wants to Be a Millionaire someday, okay, Hooke's law. Very, very common physics equation. Okay. So just store that little nugget away. Okay, so we looked at the force required to stretch or compress a spring. Now let's look at the potential energy change that happens when we stretch or compress a spring. Okay, so if we stretch or compress our spring a certain number of meters, right, it gives us a potential energy. Right, it has the potential to stretch itself back out or compress back to its static state. And here's our equation for potential energy of a spring. Okay, so you might want to write springs here on your equation sheet. This one is just used for springs. If you don't write it, you need to make sure that you understand anytime we have a K, that means it's a spring constant. So it's got to be using a spring equation. Okay? Yeah, this is going to be one of the only ones, yeah. The F equals kx, and then this one. What did we talk about the x? What is that equal? What variable is that for? Displacement. Good, and that always has to be in meters. Okay, typically we don't stretch springs a matter of meters, right? We might stretch them a matter of millimeters. So when we do spring equations, you need to be very, very diligent about your units. Okay, we're not going to stretch a spring usually a meter, right? We're going to usually stretch it 2 millimeters or compress it a centimeter or something like that. So make sure that you pay attention in your units there. I'll also make one more kind of note here for our x displacement. If I've got my spring here, okay, and then I compress it to a little bit shorter distance, right? If I compress it and it looks like this now, this x position being compressed might be considered a negative, right? If here's our origin, and I compress my x, that might be a negative, right? Because I'm going backward. But when we square the displacement, does it really make a difference? No. Okay, so just think about that kind of stuff. It is technically a negative, and then if we would stretch it out even farther, I'll go a different color here, then our displacement would usually be positive. Okay, so if we stretch our spring longer, then that displacement would be a positive. Okay, that's where we're going to stop for today.